In order to appropriately design our receiver amplifiers, we need to understand something called an effective input noise temperature, or T sub E. And so to explain this, we're going to consider this simple system where we have a source with thermal noise, which has the signal being sent into some amplifier, and then in that output of the amplifier, we have some noise power P sub n in a bandwidth B. And so what we're going to do is we are going to consider two cases. So we're going to consider the case where this temperature of our source is 0 K, and our amplifier is an actual amplifier. So we are going to have some noise produced in the amplifier. And so let's say this is going to be our case 1. So now for case 2, what we're going to do is we're going to have this same system here. So let me paste this down here. The only difference is now we're going to say, let's increase this temperature until it's T sub E in Kelvin. And now instead of an actual amplifier, let's say this is an ideal noiseless amplifier. And so we want to compare case 1 and case 2 in order to help us define this effective input noise temperature, TE. So in both of these cases, what we're saying is we have the same noise power at the output. So for both cases, we have the same noise power, which is that P sub n, at our output. And we're also assuming that our amplifiers have the same gain. So we're not changing anything other than saying that in case 1, it's actual, it's introducing some noise, and in case 2, it's ideal, so we don't have any noise in there. So again, in case 1, what we're doing is we're essentially dropping this temperature to 0 Kelvin. Of course, this is sort of a thought experiment. This isn't something that we can practically do. But in case 1, our source temperature is dropped to 0 Kelvin. So let's talk about case 1. So our temperature of source is 0 Kelvin. And so what that means then is all of the noise in the system, all of that P sub n, our power, our noise power, comes from the amplifier. Okay, and so in case 2 though, remember we have this ideal noiseless amplifier, so the temperature of the source is increased until we have the same power as in, the same noise power as in case 2. So again, because we have our amplifier is ideal, it has no noise that's introduced, what we are doing then is we are increasing, and again this is a thought experiment, not necessarily something that we would do, so increasing our source temperature until P sub n, our noise power, is the same as in case 1. And so whatever that value is that gives us the same P sub n is our effective input noise temperature. So the value, or let's just say the temperature in case 2, which is giving us that same P sub n, is our T sub E, which is our effective input noise temp of the amplifier. And so what we can see if we sort of think about this is that a higher value of T sub E corresponds to a noisier amplifier up here in this case 1. So let's just write that generalization here just to sort of give us a quick reference point. So noisier amplifiers correspond to larger effective input temperatures. And so as I said at the start, we need to keep in mind this TE isn't necessarily something that we would measure, but it's sort of a metric of our amplifier noise quality. So let's just say this is not a measured value. And let's just think of it as a metric of quality. And so with that in mind, let's look at sort of some typical values of these, of effective input temperatures for amplifiers sort of over the years. So if we go back to sort of the 1940s, when of course this type of technology was relatively new, then our TE values for amplifiers could be on the order of several thousand Kelvin. But if we look at amplifiers that are available today, we can find usually pretty low cost amplifiers with TE on the order of or below 100K. So with our effective input temperature less than 100K. So huge difference, of course, as we would expect. But what that means is, of course, that we can build these receivers so that we can receive signal levels that are very small. And again, we're going to talk about order of amplifiers, but if we use an appropriate order and we have some of these good amplifiers with a low effective input temperature, then we can properly receive and demodulate that signal. And so something I've mentioned a couple times in passing are our low noise amplifiers or pre-amplifiers. So you'll see them called both things. And I'll abbreviate that as LNA from here on out. So low noise amplifier are typically going to have a very low effective input temperature. So that's in contrast to our noisy amplifiers, which have a larger TE. And so in the next video, what we're going to start considering is, here we've talked about an effective input temperature for an amplifier, so for one component, for instance. But what we're going to do in the next video is we're going to say, well, in reality, we have all of these things cascaded together. So how do we find an effective input temperature of a system?